Alright, let's get started with this lecture video on standard enthalpy of formation. This is a quite important lecture video, so you may need to relook at this. Make sure that you solve all the problems as we go through here, and if there's any questions, make sure that you write them down and come to class with them so we can discuss them. So let's get started. First of all, let's define what standard enthalpy of formation is. The standard enthalpy of formation of a substance is the enthalpy change that occurs when 1 mole of the substance is formed from its elements in their standard states under standard conditions. Okay? So this definition is quite important and one that you really need to memorize, just like we asked you to memorize the bond enthalpies, definition of that. The enthalpy of formation is another important definition to have down packed. So again, it's the enthalpy change that occurs when 1 mole, and that's a key, 1 mole of a substance is formed from its elements. So we basically create a compound from its elements, and those elements have to be in their standard states under standard conditions. And we already talked about the standard conditions in the previous lecture video. Alright? So, what does this all mean? Well, we have a couple of example problems here. Some equations. We're going to form a mole of water here. Okay? Remember, by definition, we can only form 1 mole of the substance. 1 mole. I'll highlight that again. 1 mole of the substance. So, how do we form a molecule of water, or 1 mole of water? Well, we do so from its elements. Alright? And so, the elements that make up water are hydrogen gas and oxygen gas. Those are in their standard states as well. So elemental hydrogen, remember, is diatomic, it's H2, and elemental oxygen is also diatomic, it's O2. And they're both gases at room temperature at 1 atmosphere pressure. So those are the standard states. Now, because we can only create 1 mole of water, that means it requires, when we balance this, only half a mole of oxygen and 1 mole of hydrogen. Alright? And the energy that is produced, or in other words, the potential energy change, the enthalpy change, when we create liquid water from its component elements, we release negative 285.8 kilojoules of energy. And so that is the heat of formation, or the standard heat of formation value, sometimes known as the standard enthalpy of formation value. Alright? Now, let's take a look at another one here, right below it, and that's methane gas, CH4. So again, to form methane, or 1 mole of methane, because again, that's our definition, we can only form 1 mole of it. Methane is made up of elemental carbon, which is in the solid state at standard conditions, and again, diatomic oxygen, or elemental oxygen, which is again a gas at standard conditions. And so to balance this equation, if we're going to create 1 mole of CH4, requires a mole of carbon plus 2 moles of elemental hydrogen to produce an enthalpy change of negative 74.9 kilojoules of energy. So these two equations of the standard enthalpy of formation are good examples of this, and you're going to have to be able to write standard enthalpy of formation equations with the correct enthalpy of formation values. Alright, now to note something before we go on, this is very important. The standard the standard enthalpy change of formation for an element is always 0. So there is no enthalpy change of potential energy change when we create an element. All right, because elements are not created by chemical reactions. They're created through other processes. So we just assigned an enthalpy of formation value for an element as 0. And so don't forget that. That's important. All right, so in this box down here, in your notes, we're going to write a standard enthalpy of formation equation for ethanol. All right, and this is the delta H of formation, enthalpy of formation value for ethanol, which we'll indicate in the box here. So let's do that. So ethanol is made up of carbon. So we got to write out the elements. So carbon, which is a solid at room temperature and at standard conditions, plus it's made up of hydrogen, which of course hydrogen is diatomic and it is a gas at standard conditions, plus it's made up of oxygen, so elemental oxygen is again diatomic, and that is going to produce our C2H5OH. Alright, which is a liquid. Alright, so now we need to balance this equation. Remember, we can only create 1 mole of it. Alright, that's what's required from our definition, is only 1 mole of our compound. So if we balance it, it's going to require 1 mole of carbon, or 2 moles of carbon actually, because we got 2 of those. So 2 moles of carbon is going to require 3 moles of hydrogen and a half a mole of oxygen to create 1 mole, exactly 1 mole of our ethanol. Now the delta H of this, so the delta H of formation, and it'd be nice if you could keep it in your box, I made it too big, again is negative 278 kilojoules per mole. I'm trying to squeeze that in. You get the idea. Alright, so that is an example of writing a heat of formation reaction for ethanol. Alright, so let's move on. Now, what are these heat of formation values good for? What are these values right here good for? Well, we can use those values in calculations to find the delta H of a chemical reaction. So besides calorimetry and besides bond enthalpies, we can use heat of formation values to find the delta H of a chemical reaction by using this simple equation right here. The delta H of the reaction at standard conditions is equal, again there's our sigma, our sum of the heat of formations of the products minus the sum of the heat of formation of the reactants. So if you know how much energy that is needed or released to create one of our reactants or products, we can use this equation to find the delta H of the overall reaction. And this is simply part of what is known as Hess's law, which we will discuss in great detail in class. All right? So what we're going to do is do some actual problems here. So, for example, we can determine the standard enthalpy change for combustion of ethanol by using the following standard enthalpy of formation values. All right? So let's go ahead and work some of these out using our equation up there at the top. Okay, so in our table here, and this table right here is the heat of formation values for our reactants and our products in this equation. And so what we want to do overall is find the delta H of the reaction for this equation, which we don't know. Now we could use calorimetry, or we could use bond enthalpies like we've learned before, but instead we're going to use these heat of formation values. Alright, so let's do that. Alright, so we know that we got to start out with our products first. So the heat of formation of CO2, if we look at our table, is negative 394. But because we have 2 moles of CO2, we're going to multiply that value by 2. And then we're going to add it because it's the sum of the heat of formations of our products. And so the heat of formation is water. We have 3 of them, right? 3 in our balanced equation. So that would be negative 286, right? And then we're going to add and multiply and add, and then subtract it from our reactant heat of formation values. So we have ethanol, which is negative 278, and there's only 1 mole of those, so we just multiply it by 1. And then our oxygen. But our oxygen is elemental. That's elemental oxygen. So it has, remember, 0 heat of formation value. So we don't have to include that in our equation. So the overall delta H of this reaction, if we do the math, add everything up and multiply and subtract, we should find that the value is negative 1368 kilojoules per mole. Okay, so I'm just kind of squishing it in. Hopefully you write better than I do here. Right, so that's the value of that. Alright, let's go to our next one here. So here's our chemical reaction. Again, we want to find the delta H for this reaction, the amount of enthalpy change. And we're going to use the values that are given to us. Those are the heat of formation values. So we'd start with our products first. And you'll notice that iron is our first product. But iron is an element, so it's not part of our equation whatsoever because its heat of formation value is 0 because it's an element. So that leaves us with CO2 is our only product that we have to count in. And so we got 2 of those, 2 CO2s, 2 moles of it. So a negative 394. Alright, and so we're going to then subtract that from the heat of formation of the reactants, which we have iron oxide, which we only have 1 mole of those, so that's negative this value here. And then our carbon, which is elemental carbon, so it also has a 0 heat of formation value, so we don't include that in there. So we just essentially do this math, and we should get a delta H of reaction. So again, delta H of reaction at standard conditions is equal to 330 kilojoules per mole. So this reaction has a positive sign, so it's an endothermic reaction, unlike the other one, which is exothermic. Alright, very good. So let's go ahead. We're doing good, so let's go and do our last problem here. I don't have a lot of room here, so kind of squeeze it in as best you can. So again, we start out with our products. Water first, that's our first product. So I have 2 moles of water with negative 286 heat of formation values. Add that value to our SO2, which is 2 moles at negative 296. So there's our heat of formation values for our products. Now we're going to subtract that from our reactants. So we have 2 moles of H2S at negative 20 kilojoules per mole. And then oxygen is in the element state, so it's 0. So we don't need to worry about that one. And so when we do the math here, this should give us a delta H of negative 1144 kilojoules of energy. So the delta H for this reaction, I can do better. Write this out a little bit better here. So the delta H for the reaction, standard conditions, is negative, so it's exothermic, 1144 kilojoules per mole. Alright? So there's the answer for that. So that's essentially how we use the heat of formation values to calculate the delta H of the reaction. So at this point, there are three methods in which we have found to calculate the enthalpy change of a reaction. 1, using calorimetry. 2, using bond enthalpies, and that's the values to break a bond, the amount of energy to break a bond minus the amount of energy to form a bond. And now heat of formation values, the amount of enthalpy change of formation values that we can use to calculate delta H of the reaction. Alright? So you need to know all three methods very well. And so this is it for this lecture video.